Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about numerical differentiation. Specifically, we're going to go over a basic calculus concept, which is derivatives, right? So specifically here, we're going to talk about how do we approximate derivatives. That's something we've never done before, or at least in my experience. I've never done something like this before. And so let's recap. What's the definition of the derivative? So the definition of a derivative is this. It's actually, so given some point x sub 1, we take its derivative. It's actually just equal to the limit as our x approaches that number. And here we do a slope. So f of x minus f of x sub 1 divided by x minus x sub 1. All right, that's the slope. That's a slope. And we continue to pick points as we get closer and closer and closer to our desired point, which is x sub 1, and we will reach that point. And this is the same as the limit, and we have probably seen this in a Calculus 1 course. H means height, x sub 1 plus h minus f of x sub 1 over h. Right, so here we basically say that our x is x sub 1 plus h. And from there, we can play around with it. We can say that this is f sub x over h, right? And so approximating it might mean to ignore the limit and fill in on h as it gets smaller, right? That could be something approximating. That could be something we can do when we approximate it. What if we just ignore completely the limit and we just look at this? So approximating it might mean to ignore limit and fill in when h is small. Now, what do we mean by small? It's also a mathematical thing. Fill in when h is quote unquote small. How small is small, right? What does that mean? So, okay, let me just write it out. So it's approximately just the function at our current point all the way to our desired point over h. Or no, it's the function, the variable, and then what we have are given x sub 1, and then our h. Now, how well does it do? How well does this thing do? So if we plot, okay, let me see. How well does it do? So if we plot, here we do a log plot. Since I'm a Filipino, log means, in my language, Tagalog, it means falling down. But here it means logarithms. So if we plot a log plot of the error, so here now we're identifying the error. So we're doing an absolute value of my derivative minus that thing, the approximation. This is like this. Or actually, let's write that f of x1 plus my height. Then f of x sub 1 minus h, or divided by h. So how well is that? How low is that error? Well, if we were to kind of plot it, this is how it would look like. Say we're in the first quadrant. It would look something like this, right? And so here, what is happening? But that's what we see, right? Even I'm feeling confused when I see this. Okay, let me just write down what the parameters or what the coordinates are. Then I think this one was 10 to the negative 7 or around, oh, I'm kidding, 8. And then this was 12 and 10 again. Okay. And then here this was 8, 4, and 0. Okay. Oh, this 8 is specifically here. Then this 4 is somewhere there from 12. So it's maybe like there. Okay. So what does this tell us? Well, let's do an error analysis. We can use this idea of Taylor approximation, right? Let's analyze the error or error analysis. Let's use Taylor approximation. Okay, this is something I'm gonna explore literally right now because this is the first time I've seen this. So what are we gonna do actually? Oh, we're going to see how this function behaves. F sub x or f of x sub 1 plus h. Okay, yeah, we're gonna see how it behaves like with variable h as it's around 0. Behave like when my variable h is around 0. Right, so that's what we're gonna do. So here's how they do a Taylor series. This is equal to, well, this. Oh, wait a minute. So it's f, okay, let me just copy, plus h of its derivative. Why is that? Anyway, we'll see. Plus h squared over 2. It's double derivative or double prime. And then 3. And then I think this is a factorial. 3 factorial f double prime of x1. And then I keep on going. So this is h to the 4th over 4 factorial, double derivative of this thing. And I keep going here. And this is just equal to, okay, let me write the full thing. So this is f of x sub 1 plus h f prime of x sub 1 plus h squared over 2 f double prime x sub 1, and then 3, but this time with the factorial. Yeah, so that's a algebra thing, factorial, all the way to some value here. This is, oh, what is that? H to the n over n factorial. And then f Oh. Oh, wait a minute. Oh, this is three. Or yeah, this is three. Triple derivative, and then this one's also three. Oops, my bad. Yeah, and then so this is gonna be four. And so this is gonna be nth derivative. Here, I don't think it says it's x1. Here, it's kind of like something else, a placeholder, blah, blah. And this placeholder is, or it belongs to, wait, it's not a real number. It's a column vector, apparently, x sub 1, and I'm adding it to x sub 1. I can't see that. What does that look like? X sub 1 plus n? What is that? It looks like an R. Not sure what that is. For F, mo okay. Yeah, I cannot see that. I think this means for x sub 1, x sub 1 plus h, or something along those lines. And we're saying that this, I don't know what that's called. That's the error term. We call that an error term. And it exists for F. Okay, now I can't read. F small, F smooth. Okay, it's an error term. Okay. Anyway, so we have that, and then we basically fill it in. So here we're gonna fill everything in. How would that look like? So here we have our limit definition, right? So f of x sub 1 plus h minus, so this is our approximation already because there's no limit. This is a Taylor approximation. So f of x1 plus h f double prime f sub x1 plus h, or my bad, it's f prime. My bad, my bad. So this is f prime. Then that's h. So now we do squared over 2. This is f double prime of x1. Or what in the world? I cannot read that. It looks like a 2, but then it's not. Or it's some random term that I don't know. Oh, it's the error thingy. So what's the error like if we approximate it there? Minus this over h. Okay. And here we say that, oh, okay. And then here we say that thing is an element of a vector, I believe, that consists of these things. And then here we just say, okay, f prime of x sub 1 plus h over 2 f double prime, I think, of this error thing. And so if we get the norm, or yeah, if we get the absolute value of this thing minus my approximation, oops, Well, this is just equal to h. Oh, it's equal to the error. The one with the error term divided by 2. And here we even looked at its complexity, which is big O of h. And we had a what? We had a prime. That's interesting. And so here we can say that we have a convergence route. Oh, that's what it means. So it's not okay. Let me. So this means we have convergence route. What this means is I think it basically this will converge to some value as we keep on doing a Taylor approximation. Here we assume that this is a number, but it might be giant or it might be a big number. So it might be a really, really, really big number. And so we can see in the plot, in the previous plot, let me just go back to here. In this plot, we see that for h large, when as our h is big, the error behaves like O of h. But then for very small h values, it goes back up. And so this is due to rounding error in the computation of f of x sub 1 and f of x plus h. A computer actually computes 1 plus s1 f of x sub 1 and 1 plus s2 f of x sub 1 plus h. And with s sub 1 and s sub 2 small and on the same order of magnitude, but we don't know its value. So typically s sub 1 and s sub 2 are approximately 10 to the power of negative 16. And a computer actually computes that thing. Okay, let me yeah, it's really hard when there's no coding involved. Yeah, this is hard to understand if there's no coding involved. Hmm. And then we see a convergence rate and stuff like that. Okay, let me go ahead and do this. So when h is large, the error behaves like O of h. This was a very, very, very big number. Let's say like 1 to 1,000, I don't know. H was a very big number. Then its complexity is linear time. Oh, if my h was big, it's linear. But if h was small, then it's this thing, right? And that's due to rounding error in the computation. And so what a computer actually does, here's what a computer will do, is it will do this, 1 plus s sub 1 times our function. And we also do this. So this is what a computer will do. I'm going to explain what S1 and S2 are. S1 and S2, they are small and on the same order of magnitude. But we don't know their value. They are numbers though. So here we say that S1 and S2 are small and on same magnitude. right? But we don't know its value. So for a computer to do this, let me just, here's what computer will do. 1 plus s sub 2 of this function minus that 1 plus s sub 1 of my original. I divide that all by h. This is actually just equal to my approximation. And that's the worst case. Let me see. Oh, so it's this one plus my S2 and S1. S2 of this, S1 of this. And the worst case is that, so we have a worst case here. Worst case is my S2 is equal to S1. And that would be 0 or something like that. If they were the same numbers, how would that? Not sure. I'm still not super sure. Approximately, this is just my derivative, or it's actually my Taylor thing. H of 2. Then there's my error term plus 2s2 or s sub 2 over h f of x sub 1 for h small, right? Why did I write 1? For h small. When we have a small h, then that means this output is equal to our original. And from here we have 2 errors. So one is from not taking the limit, and then we have a rounding error where s sub 2 over n. Okay, let me see. Oh yeah, so those are the 2 errors, right? So mainly the 2 errors are not taking limit. So this is this thing, h of 2 of this double thing, right? I think it was h squared, right? Or no, it's not. Yeah, so if we don't take the limit of that, and we also have a rounding error. Specifically here in, what was it? S sub 2 over n, or over h. So in the plot, we see that at first for large h, this one dominates, right? And so we have a line. And then out at h, when it's equal to 10 to the negative 8, bad errors are on the same magnitude. So if it's less than, the rounding error dominates. And so does a method with a higher convergence rate count? Well, yes, right? Okay, let me just do this. So here if we say if my h is basically greater, or it's equal actually. If my h is equal to 10 to the negative 8, then this thing dominates. But the moment my h is less than that value, well, now this thing dominates. So there's a convergence rate here. Okay. And the center difference scheme. So we actually have a new thing here. So there's a method with a higher convergence rate count. Yes. So the center difference scheme, we show that the convergence rate through Taylor polynomials. Okay, let me. Yeah, it's a lot of proving, to be honest. So we have a center difference scheme. Here it's f of x sub 1 plus h minus f of x sub 1 minus h over 2h. Then we show that convergence rate through Taylor polynomials. Yeah, so we do a Taylor polynomial of both of those things. And from there we have that. And we have oh shoot. We have like a large derivation of Taylor polynomials. And this is just basically, so through Taylor polynomials. This is just the same as its derivative plus that. And we see here that 2 is a convergence rate. So it will converge at a rate of 2 units. And the error will go down at a faster rate. Okay, so I'm gonna be honest, I was completely lost with some of the parts. I might have to do an in-depth review at some time, just so that I can, or break these down into steps. But as of now, I'm just trying to get a glimpse of what exactly this is. So in my own words, right, this is basically how do we approximate derivatives and how do we analyze error using derivatives, right? And so here we came to the conclusion at the very end after some calculations. Well, we can use derivatives to bring down the error at a faster rate, right? Because that's calculus, it's analyzing change and stuff. And so we can use calculus, in this case, numerical differentiation, to analyze and bring down an error. That's it. That's all I can say about it. So yeah, pretty much that's it for today's video. And I'll see you all in the, yeah, I'm gonna do another part of this where we're gonna be doing more approximation of derivatives. But yeah, I hope you guys enjoyed and learned something, and I'll see you all in the next one.